Hello. Hi guys, good morning. Welcome back to a new video. In this week's problem, find a subarray with bitwise and closest to k. Spoiler alerts. People who have watched two-pointer crash course and segmentary crash course and bit manipulation crash course and binary search template or a fenwick tree, again, either a segmentary crash course or a fenwick tree crash course, either one of them, you are good to go to understand or to also think from yourself all the approaches. What every crash course we have taught and how they're useful is, in this we taught the properties of AND, which is directly applicable to this problem. In this we taught where all you can apply two pointers and sliding window, and also the template which is directly applicable in the most optimal solution. In this we taught the most optimal least modified code of a segment tree which you can use, which I will show you exactly same code using it. This is for the interviews, that if you want to write the same functionality as that of segment trees, but yeah, not all, but yeah, most of them, and especially not using range updates and stuff, although you can do it range updates, but still, to keep it simple, if you had watched it, you can simply solve by using a fenwick tree also. Last but not least, we will merge segment trees along with a binary search. So binary search template, you should have watched it. Now, coming on back, after I hope so you have watched all these 5 videos. Again, these 4 are the crash courses. This is the binary search template. Coming on back, what the problem says. Problem simply says, if you would have watched it, I'll highly recommend pause it and try by yourself. I'll give you a very big hint to solve everything. Now, it simply says that you are given an array nums and an integer k, and you need to find a subarrays of nums such that the absolute difference, modulus, mod, as in the math mod, sorry, not the math mod, but the English mod, which is also called as absolute. The difference between k and the bitwise AND of the subarray of elements is as small as possible. It directly or indirectly says, take a subarray from L to R, do a AND operation, bitwise AND operation for all of that subarray elements, take a absolute difference with k, which is given in the input, and whosoever is giving that minimum difference is your answer. Cool. So very basic brute force approach is, bro, I have this, I need to generate all these subarrays. So what I will do, I will take the brute force approach, generate all these subarrays from L to R. I know generating all these subarrays I to j or L to R takes O of n square time. After I have one subarray, I will generate its AND by simply taking on the for loop from L to R, and then it will take a O of n time, and thus O of n cube. We know there's a standard optimization of a normal brute force when you generate on the subarrays is, while generating the subarrays, make sure to generate or to find the AND of that subarray also. How we do it? We know that when we generate a subarray, we actually have our I fixed and we go on to j. Okay, then this j, then this j, then this j, and so on and so forth. So while you are at ij, find the AND. Okay, then go on to next j, just add up this AND. Okay, AND with nums of j, existing value, existing range AND with AND of nums of j again, and thus while generating the subarray itself, you can also find your range AND, which will remove this extra AND operation of O of n, and thus giving you a O of n square time. Still, this will fail for this problem, O of n square. How to optimize it? Let's look at very closely what we were doing. We were saying, Aryan, I have some specific I or a specific L. For that, I was trying for all the possible R's. That is what I was trying when I was trying this brute force approach. Now, if I was trying this, which means I will have to go on to all the possible R's, which I don't want. I have to remove something. Okay, let's imagine that I'm taking L and I want to get rid of all these R's. If I want to get rid of all these R's, I have to firstly understand what I wanted. I wanted my bitwise AND for the specific R which could have been there. I want a bitwise AND from that L to R1 as close as possible to my digit or number k. Look closely. We are firstly using a bitwise AND here. So I hope you know the property of a bitwise AND, which is again bitwise OR property, AND property, XOR property. All of them are taught in this crash course, which is very important. Now, if you know that bitwise OR AND is always decreasing. It is always decreasing. And again, whenever in the video I say decreasing, I mean it is non-increasing. I specifically will say decreasing. Again, if you will say, Aryan, I will take 3, 3, 3, and is always 3, bro. That's the reason I say, when I say decreasing, I always mean non-increasing. It will either remain constant or will decrease. It can never increase. Cool. So now let's come on back. What we could infer from our crash course? We could infer that L to R1, if I have some AND in this range L to R1, if I move on further to R2, it will only decrease. If I move to R3, L to R3, it will only decrease. So my AND will only and only keep on decreasing. Entirely again, everything with example and stuff, you can just go and watch the crash course. So we realized if I have some L comma R0, this dot, this point represents and range and value from L to R0, or you can also say L to L. This L to R1, this dot represents range and value from L to R1. This dot represents range and value from L to R2. This dot represents range and value from N to R3. And I can easily see it is decreasing. It will keep on decreasing. So we realize that it is always decreasing. Now, if it is decreasing, we get to know something. It is a very big hint that if you remember, we wanted a few things. Let's come on back. We wanted something to be as close. This AND should be as close as to K. And I know that this AND itself is actually decreasing. Let's club the conditions. So we realize that for a specific L, for all the R's going ahead, I know the AND value will always decrease, and I want something to be closest to K. It is the same problem saying search the closest number K in a sorted array. I know my array is sorted now. I have to search for a closest number in this sorted array. This array is basically representing the AND of ranges from L to R1 to R2 and R3 and so on and so forth. I want the number closest to K. That's a simple either a upper bound or a lower bound. You can search, or you can do a binary search from yourself also. So again, if you don't know this, just go and watch the one above video which I told you of binary search. So we realized for a specific I, if you remembered, I told it, this is I have fixed it. Or you can say right now for a L also, I want to find, again, these bars, these white bars represents range and from I to this point, then this represents I to this point, this represents I to this point, and so on and so forth. So for me, I have to do a binary search on this range. I know it is decreasing. So I will do, okay, I'll take a L and R again. So as not confused, I have fixed this I index and I was trying to find all the J's. Now to not find all the J's, I will search for an index which will give me the closest index, or basically closest value, which is as close as to K. So L, R, I'll find the mid, and then if I find the mid, now the simple operation binary search is you just have to move either right or left, which means you will have to either move left or right in this range. Firstly, let's see what we are finding. We are finding the range and from I to mid. I am finding the range and from I to mid. So first very basic stuff which could have come to your mind is, Aryan, how will I find the range and from I to mid? You know, for any range operation and or XOR, I can simply use my segment tree. And why I am saying segment tree, you can also use your fenwick tree if you want. Cool. Now, if I come on back, and again, segment tree, we will use it in the code because it is just a one line change from the template which I have given you. Cool. Now we will get the range and in this range easily from I to mid in a log n time, because I know the length can be at max log n. So I can get the range and in log n time. Now when I have the range and from I to mid, okay, you have the range and. Now your task is where I should move my window. If you know this is the range and, if this range and is more than equal to K, or I can say more than K. If it is equal, I am very good, because if it is equal, I can simply return 0 as my answer. But even if I put a equal, that will not hamper me, because it will just go 1-2 points here and there, or else it can return a 0. But still, I'm saying if you want to optimize much more further, a little bit further, you can also put a else if. Again, this is else if, and this will be else condition, that okay, if the range and is actually equal to K, simply return 0 from here itself. 0 is the most optimal answer. Cool. Now we just took else greater than equal to K. If my range and is more than K, this range and is more than K, For sure, I would want to reduce my range and. How to reduce my range and? Range and will reduce only when this window will increase. Because I know the more elements I will take, the lesser and will become. So if the range and is high, so I have to decrease my range and. To decrease my range and, I have to take more elements, which means I have to increase my range length. Now I know my range length right now is from L to R. I have to decrease that range length so as to shift this mid rightwards. To shift the mid rightwards, I have to make my L point to mid plus 1. I'll make my L point to mid plus 1. Else R equal to mid minus 1. Again, if you're confused, Aryan, what about L less than equal to R? All that things, why L equal to mid plus 1 and why not L equal to mid? Go and watch our simple binary search template video. You'll get it. We always use the same thing. Now, coming on back, we have simply figured out that we can easily find the range and when we found the range and from I to mid, I can simply use my binary search, this binary search, to move my L or R just to shift my mid so that the range and from I to mid will become as close as to K as possible. And if I have got my range and from I to mid as close as to K as possible, I know starting from this I, the closest I could reach, the closest and range and I could reach was this range and, right? And thus I will try for this. I will try for this as for all the i's. Okay, I will go on to next I. Then again, I will find the closest and starting from this I to anywhere, I'll find the closest and range and again, I'll just try for all the indexes I. And that's the answer for me. So you realize this range and will take a log n time because of my segmenting or a fenwick tree. And thus I am doing a binary search on that specific range and again, so it will take again a log n time. Let's see the code. It's pretty simple. Firstly, I show you a quick thing how to find the range and. Only code change which we had seen, you'll see the only code change in the template which I have given you for segment tree is that we have made a node class which will represent every node. For me, every node is an integer, so I'm okay. For every node, I have only one integer, which is v. For me, the identity element, if you don't know what it is, go and watch the crash course. For me, that will be all ones. All ones. It will be all ones because it will not change my value. This is anything which does not change my value. Okay, when this is done, I will simply go on and make my merge functions. If I have two nodes, how I will merge them? I know I have to do an AND operation, so I will simply put an AND operation. That's it. These two lines was the only change in your segment tree code and you're good to go. Because we don't have any updates, so this you don't need to change at all. So you can see its default values, it will never be used. You can put a or and anything, it will never be used because it will never come on to update anyway. Now in the code, we have some initializations. Again, I remove the redundant, lazy and unpropagated. If you want, you can keep it, but I'll say remove it because Leetcode have a very tight constraint some way, like somehow. I am telling this why, because I had to remove, if you know, in the template we had shared constant int and address of v, which means every integer I was passing in as a constant integer reference to that variable. When I was putting it, my complexity was reaching to 1642 milliseconds. Right. Again, this is not by Leetcode's runtime. I have my own timer from which I actually have like a simple code in which it gets the time in microseconds and then I just get it on Leetcode as a code. But when I remove the constant and address, it started giving me 240 milliseconds, right? So I'll say for Leetcode submission, make sure please do remove the constant and address, so as to pass everything by value. Although this constant int address, or basically reference of a specific variable, it is very much useful for maybe big nodes. If you have a node, you are passing it, for example, in this case, if you have update, you pass it by reference, constant int reference. It will be useful, but for integer, it's a primitive type. So for that, a copy is much more cheaper than passing by reference and then dereferencing it. So you can take integer as it is. Although if you just use in code forces and stuff, it would not have given a TLE at all. But I saw that when I was putting as a constant an int address, it was giving a TLE because passing by value is much more cheaper than dereferencing actual variable. So again, same code as it is. I did not touch it. I removed this code where it was not useful. If you want to keep it, you can keep it also. Same code, exactly same code. Now coming on to our main function. It's simple. I firstly build my segment tree, then I build my nums, then I went on to all of my integers. For every I will go and check. Simply do a binary search. But before that, if my nums of I is less than equal to k, if my nums of I is less than equal to k, which means there is no point if nums of I, you know that if you take a range from nums of I, it will only decrease. The range and will only decrease. I am saying this nums of I is already less than k. If it's already less than k, which means that nums of I can never increase. It can only decrease. So this is right now the closest. Nums of I is closest to k right now. If you will do more AND operations, it will only decrease. It will only go away from k. So if my nums of I is less than equal to k, simply take the minimum right now itself. Now, if nums of I is more than k, if it is more than k and your k is here, then you can take a range and which can make it come close to k as close as possible. Thus, from I, you will simply apply a binary search. You have taken L as I, so this is my L, this is my R is equal to n minus 1, and then again R, then simply apply binary search template where L is less than equal to R, find the mid, find the range, and in the range from I to mid, find the range, and if the range and again minimize your minimum diff, that's your answer. Minimum diff is your answer. If the range and is less than k, simply have R equal to mid minus 1. If it is more than k, R equal to mid plus 1. Or you can simply say as else if range and if it is more than k, then R equal to mid plus 1. Else then return the 0. That's it. That's also completely fine. A bit more pruning in your code. Now, when the binary search is done for a specific index I, you have got the minimum diff whatsoever you could have tried. Just try for all the i's and get the answer. Thus, you see, for every I am firstly doing a binary search, which will take log n time. On every binary search, I am again doing a range query, which will again take a log n time. So it will be O of n log n square, and space uses O of n. Now, can we improvise it? It's a good question. And for sure, for the folks who don't know segment trees and stuff, they might be a bit, Aryan, please optimize it. Yeah, for sure, let's optimize it. So optimizing, simple thing. If you had watched a simple 2-pointer crash course, you would have seen in this we saw problem, subarray sum equal to k, which means you have to find the subarray sum equal to k. Or you can find the longest subarray also, and so on and so forth. There are multiple variations for this problem. Now, I can simply tweak it and say find the subarray sum closest to k. Right? That's also possible. I can same way tweak it as saying find the subarray and closest to k. Why and? Because I know the and operation was monotonic. That from I to j, if I have this and, if I move my j further, and will only decrease. If I move my I further, and will only increase. So I know if I have this window, if I move my j, my and is decreasing. Move my I, my and is increasing. So with this movement of I and j, which means a sliding window or 2-pointer, I can make sure I will try to bring my range and as close as to k as possible. Cool. So I had this array. I will simply take again same way. I will take two random points I and j. This is my current window. And we know in our standard template of binary search, sorry, our standard template of 2-pointer, it simply says that you have 2 points I and j, while j is less than n, do something, which means for the element j, which you have got recently, incorporate that in your variable. For me, the variable is range and. So I will simply add this element in my range and. Again, I have written an and. Don't go into and directly. Please don't write a plus. It is an and operation, but I'm simply saying incorporating nums of j, right? Then make sure to minimize or maximize the answer whatsoever is your task. For me, the task is to minimize my answer. I minimize it. How I will minimize it? Minimizing the minimum difference with what? For me, I want to minimize my minimum difference with k and the current window and, which is the range and. This is what I need to minimize. Again, make sure to take an absolute value. Absolute value. Now, when this, again, minimizing, you can do it every step. Now, for you, you know that at every step, you always increment your j. But we also have seen in the simple sliding window or a 2-pointer that if we surpass our condition of whatsoever we have, then we keep on shrinking our I. At what point I will shrink my I? I will shrink my I. Again, we know shrinking I will increase my range and, right? So if my range and becomes less than k, start shrinking my I. Again, while I is less than j, which means shrink my I, which means remove the existence of nums of I from range and. Make sure to minimize your diff again and make sure to increase your I. That's a standard template of our 2-pointers, right? Now, we use the exact same stuff. And we know why we can use it, because we know that our range and is monotonically decreasing. We increase our j, range and will decrease. We increase our I, range and will increase. Make sure always I say range and will decrease. Decrease means non-increasing. Increase means non-decreasing. Cool. Now we know that at every step, my main bottleneck is Aryan, how are you doing this addition and subtraction? Because it is not a normal addition. It's a and. In the range and I want to incorporate and of nums of j. In the range and I want to remove the contribution of and of nums of j. So how I will do it? Simply let's visualize what is happening, what we are maintaining. For sure, whenever we deal with a bit, we actually bit operations, bit manipulations, we deal and come down to the bit values or bit representation of a number, which we have already seen in our bit manipulation crash course. So we will see that, okay, this is something. I will start representing every number as a bit. Okay, 1 0 0 1, 2 0 1 0, 4 1 1 0, 5 1 0 1. Now, maksad nahi bhulna, your main aim was to find the range and. If I will take a range and of this, so in general, whenever we take a prefix sum or something like that, we take the addition or the contribution of the bits. Okay, 0 is coming one time. Okay, 0 1 1 will come on the this bit, 1 0 1 and 0 0 0. So if I do a range summation, it will give me a 1 1 0. Does this represent a range and? No, it represents my range or. This represents my range or. And for your curiosity, if I take one more element like this, 1 1 0 1, so 1 0 1, let's take both of them, I will get a 2 1 1. This represents how many times my 1 is occurring. Again, this is again representing my range or. Why I am saying is because whenever I want to shrink my window, I want to, let's say, remove this contribution. So I will come on here and I will remove, bro, you had 2 1 1 current window, remove a 0 1 0, you will get a 1 0 2, which will represents, okay, 2 0 1, which means this bit is set, this bit is set, this bit is not set, this bit is set. If you take the range or of this range, the first bit is set, the second bit is not set, the third bit is set. That which infers that if you take in consideration 1 and then if you take the range summation, then you will actually be incorporating your sliding window for a OR operation, but you want for an AND operation. Simply reverse the process, which means earlier you were taking 1 in consideration when you were doing a prefix sum, kind of. Let's take 0 in consideration, which will tell you how many zeros are there at that location, which means when you had a 1 0 0 1, 2 0 1 0, 4 1 0 0, 5 1 0 1. Let's invert it, as in whenever I have a 0, I will count its occurrence or the frequency as 1 0, as you can see, 1 0 1 1 0. If I have 1 at the location, it means I have 0 0 1 1 0 0 1. It is just so that I want to count the number of zeros at each location. Why it is important is, for a AND operation, if I have the count of number of zeros at this bit as 0, only then I can say that this bit is set after doing the AND operation. If the count of number of bits set at this location is more than 0, which means I have one or more zeros here, which means ultimately if I do an AND operation, 0 will for sure come here. That's the reason I'm maintaining the 0 count rather than a 1 count. So when I've maintained the 0, so for me, the 0 is existence. Now, I can just show you how I can represent that. So I will simply show you the perfect sum. So you can see 100 as it is. Now 101 I added here and thus got a 211, representing I have 1 0 at the first bit, or I can see the 0th bit, 1 0 at the first bit and 2 0 at the second bit. Again, prefix sum representing 2 zeros at the first bit, sorry, 0th bit, 2 zeros at the first bit and my 2 zeros at the second bit, and thus so on and so forth. This is just to showcase that how I'm representing my range and in a window. Aryan, but how you represent as a range and? If I ask you what is the range and of this window, you will simply say, Aryan, I will take this. This represents that how many number of zeros are here. If I have a 0 here, so I will not contribute that in my value. 0 here, not contributing. 0 here, not contributing. So if I take these two, and again, these two I have taken as it is. If I take their and, if I take their range summation, if I should say, as you can see, 1 will come here, 1, 1, 2 will come here, 0, 0 will come here, which represents that on the 0th bit, I have 1 0. So this will not contribute in my answer. On the first bit, I have 2 zeros. Again, this will not contribute in my answer. On the first bit, sorry, on the second bit, I have 0 number of zeros, which means it will have a 1. It will have a 1 here. So if I ask you what is the range and is 0, 1 and 2. 0, 1, sorry, 1, 2 and 4. Range and is 4. So if you go back and see 4 and 5 representing a 101 and 10, sorry, 100 and 101. 1 will come as a range and both will come as a 0, 0. This 0 have a count of 2, which represents 2. 0 have a count of 1, which represents 1. And that's how I can easily go and incorporate my range and. Cool. And that's what we will do. We will maintain the window. For me, the window which I will maintain in a slide window, you maintain a window. That window will actually represent the bit. That bit, its frequency will be the number of zeros at that index. At that 0th index, first index, second index, and so on and so forth. Right? And that's the ultimately code. Cool. Now the code, if you go into the code, again, it's very simple. Same logic of our sliding window we will use. If you're confused, please go and watch this with the diagram. Everything is here. Now coming on back, we'll come on to our bit. Firstly, I and j and range and. Again, I and j simple variable which we take always. Range and is the current range, current window. For me, this is the window. If this is the window for me, what's the range and of this window? Cool. This bit will maintain this kind of a frequency of all the bits which are 0. So bit of I represents the count of zeros at the ith bit, not ones, zeros at the ith bit. And why? And we realized why we cannot take ones but zeros. Cool. Now simple sliding window, while j is less than n, j plus plus, right? Simply add the current element nums of j. Add the current element in what? Okay, you are maintaining this window. This window is bit. This window is bit, and its result is the range addition. Is its result the bit window which we have? Its result is range addition, but this window is actually bit. So if this window is bit, simply add the element nums of j in this bit. What I will do, I will simply go and add the nums of j, which is this element, in my bit. I'll simply go on to all of my I equal to 0, I equal to 1, which means 0th bit, first bit, second bit of my element. If that bit is set, how to know that? Right shift. But again, if you are confused on these operations, go and watch bit manipulation crash course. So I'll just simply check if that bit is set, if the ith bit is set. If it is not set, then you increase your bit of I, because if the ith bit is 0 in element, then I increase my frequency in my bit. And thus again, when I have added my nums of j in my element or in my bit, I will have to find what is the range and value. Range and value of the current bit. Bit is the range. For this window, bit, it represents the ultimate and value. So okay, go and find the and value itself of this range. So I will pass bit and I will go and ask the and value of this bit. Bit represents window for me right now. So I will go and ask for this bit, iterate on all of the bits. If that bit of I is 0, which means the count of number of zeros at the ith bit is 0, which means that is set. If that is set, only then I should incorporate that in my answer and thus get my answer for the window, which is bit. Now again, minimize your answer from the range and minus k, and then make sure if your range and is less than k, simply try to shrink your window, which means move your I. How to move your I? Subtract the nums of I from your window, then make sure to get the new range and of the current window, which is bit. Incorporate that in your answer, minimize your answer again, and then make sure to move your I because you have shrinked the window, and keep on doing it until you have your range and less than k. And again, if I go to this subtract element, same as that of and, just that you have to go into all the bits of this element. If that is set, no worries. If that is not set, then decrement its count because bit will store the count of zeros. That is how I will get my subtraction done. And thus ultimately make sure you can do it, or if you want you can just put it in the end also, it's not required, but yeah, just to prune the answer. If the minimum diff is equal to 0, that's a minimum possible value which you can get, so simply return the 0 and that's your answer. With this, O of n time in your sliding window, O of 32 time for all these add element or calculate window or subtract element operations. So complexity wise, it is time of O of n into 32 with the space of just 32 because of this bit or the window space which we have taken. And that's the most optimal approach. For me, the first one was the most intuitive and the most easiest one. But this one also, when you have, maybe again, I don't know why this did not strike me first, but the segmentary one, it struck me first. But yeah, this is also more or less same. Or if you don't know segmented, then this is much easier. Cool, bye bye, take care. I hope you guys got it. If yes, then please do smash the like button. It will be really helpful. Bye bye, take care. Bye. Like kar dena yaar. Share kar dena if you want. I know people don't do it, but if you can, please. Bye bye. Bheek मांग रहा हूँ यार मैं, पागल हो गया हूँ.